In this part, we will discuss memories and bidirectional IOs. Memory is a two-dimensional array of flip-flops of memory elements. Okay, we talked about registers. We said that a register is a collection or a vector of flip-flops, meaning that if I put 4 flip-flops together with a common clock, a common reset, and have inputs and outputs, then this becomes a 4-bit register. Okay, well, that's fine. And then if we put 4 4-bit flip-flops together, or an array of 4x4 flip-flops, that becomes a memory. Of course, memories are various types of them. For example, we have static RAM, meaning that they are static, meaning that the when you clock it, you put some data in it, it's there, and it's there for as long as the power is there. We also have DRAM, dynamic RAMs, meaning that they have to be refreshed every once in a while. We also have ROMs, meaning that you have written into them once and you can only read from them, which is read-only memory. We have non-volatile memories, meaning that the memories are written into, and if the power is removed, you still have the contents available. Generally, we are not trying to discuss various types of memories here. All we are saying is the main concept of what a memory structure is. Large memories in the order of some 10,000 or 1K, for example, array of memory, that's called a memory. But then short memories like 128 bytes of the data storage, that's more like a register file. And memories have addresses, meaning that there is an input, let's say a 10-bit input, that addresses various locations in the memory. And word length for a memory is referred to as how many bits each entry in the memory is. So if, for example, I have a 10 lines of address, 8 lines of output, meaning that the entries in the memory are each 8 bits, then we have also 8 bits of input, meaning that you can write 8 bits into the memory, and then 10 having the address bus length of 10 bits. That means you have 2 to 10 various locations that you can address, which is 1024. Okay, so what I'm showing here on the right hand side is a memory with a read bus or an input bus, an output bus, okay, and an address bus, which is 10 bits. The input bus is 8 bits, the output bus is 8 bits, the address bus is 10 bits, and here you have 124 8-bit words that you can read or write. Okay, reading can be done by issuing a signal to the memory for read, and writing is it can be done by issuing a signal, putting a 1 on an input, which is a write. Sometimes instead of having a signal for read and signal for write, what you have is a read-write bar, meaning that if it is 0, it's a write. If it is a 1, it is a read. If the read-write signal is only 1, then you also have another signal to indicate that you are reading from the memory, or you are actually selecting the memory for read or for write. So let's look at it this way: read-write bar. That means if it's a 1, it's a read. If it's a 0, it's a write. And also another signal for selecting it, which is referred to as chip select. So here on the right hand side, I'm showing a memory as a memory with chip select, with a read-write bar, 8 input lines, 8 output lines, and 10 address lines. What I'm showing here is a memory with in address lines, M input lines, and M output lines, and this is 2 to N M-bit memory. And we can have clocked memory. We can have memories that you select and you hold the address for some amount of time, and then the reading or the writing will be done. The memory structure I'm going to be showing is a memory that is primarily built out of flip-flops, and let's look at this situation here. I have, just to make it simple so that I can show the entire structure, I have words that are only 3 bits, and I have 2 address lines, meaning that I have a total of 4 3-bit words. Going back to this thing here, I have 2, N is 2 here, and M is 3 in this structure I'm showing. The memories don't have to have both input and output lines. They can actually share input and output lines. Sharing means that instead of having 2 8 bits in this case here, they have one bus that can act both as input and as output. When read-write bar is 0, the bidirectional lines will be acting as input for reading, and when the read-write bar is 0, the input-output lines will be acting as when the read-write bar is 1, means that the memory is being read from, so the input-output lines become output. When the read-write bar is 0, that means the memory is being written into, and therefore input-output lines are treated as input to the memory. And this is this situation here. You have 3 input-output lines, and you have 3 state structures. And then you have a read-write structure, which has a chip enable or chip select and a read-write bar. Notice here, if the chip select is active, that means there is a 1 here. Read-write bar is 1 here. There is a 1 here. If there is a 1 here, this input to the tri-state structures is 1, and therefore you will be driving these I/O lines with the contents of the memory. Now, I haven't talked about selection of the specific words yet. These are output lines that, depending on which word is selected, will be driven by that specific 3-bit word. On the other hand, if I have a if chip select is still a 1, okay, and read-write bar is a 0, then these are 0, and therefore these are 0, and therefore you will not be driving these in-out lines with the internal outputs of the flip-flops. Instead, you will be driving these lines into the memory. And notice that these blue lines become the inputs into selected flip-flops. Alright, so what you are really seeing on this side here, let me just show it as a separate line here. Let me also use the same direction. So this is inside of the memory. Here I have an I/O line, and the I/O line, this is the I/O line, and then there is a tri-state. Okay, coming from the outputs of flip-flops, and then this line goes into inputs of flip-flops. Okay, and then you have this line here that can be either a 0 or a 1. So let's do that again. If this line is a 1, this is how the outputs of the flip-flop will be driving the I/O line. If that line is a 0, okay, then this tri-state will be open, and therefore you will be going from here into the inputs of the flip-flops. Alright, that part is called the I/O block, and now let's look at the individual words. Depending on the address, there is a decoder on the left hand side. The decoder, depending on the address, selects one of these lines here. Let me use a different color here. I'm going to be using this color here. So let's say the address is 10, meaning location number 2. Location number 2, if the address is this line is going to be active. Okay, that line being active versus all other lines. So this means there is a 1 here, there's a 0 here, there's a 0 here. Remember, this is a decoder. There's a 0 here. And the line that is active causes the tri-state gates, this, and this. This is, by the way, the horizontal line I'm drawing is the word line. This word line causes the output of the flip-flop to go on this line here, to go on this line here, to go on this line here, if this is being read. And at the same time, if it's being read, this read-write block causes the red line to become the output, and therefore what you are seeing on row number 2 will be driving the output. On the other hand, if you're writing into the memory, this red line will not be acting as output. Instead, what happens, this word line that you have here, this word line that you have here takes this word line that you have here along with writing. That means there is going to be a 1 here, and enables each of these flip-flops for being written into. So there is a 1 here, and because of the writing, there is a let's follow this line here. Let's follow this line here. So there is a 1 here, and this line, I'm going to show it to you with highlighter, and then I'm going to be removing it to keep the picture okay. So a 1 here will cause a 1 on the input of the AND gate, and there is already a 1 on the decoder output, and therefore the output of the AND gate for this entire row becomes 1. These becoming 1 enables the clocking for writing into these flip-flops. And then as soon as the clock arrives, notice that since I have I'm writing, and since I have a 0 on these tri-states, therefore the blue line, the dark blue line, will be conducting and bringing data for me into the flip-flop, into the D inputs of the flip-flop. Okay, so this is what's going to happen. I'm going to use this color, and therefore, see, this is going to be coming in through the D input. This is going to be coming in through this D input. This is going to be coming in through this D input. Okay? And then when you're writing, as soon as the clock arrives, you will be clocking your data that you have on the I/O lines, now acting as input into the memory. You will be clocking the information into the flip-flops. Therefore, for reading, you don't need a clock. All you need is a 1 on read-write bar and a 1 on the chip enable or chip select. And you will be reading through the red lines. Let me also show the red lines when we are doing the reading. Okay, and when we are and then in both cases, read or write, it is necessary that the word line or this line over here is a 1, so that the flip-flops are either enabled for clock, or flip-flop outputs are putting their data on this vertical line. These are called bit lines here. All right, that's generally a memory structure, and obviously memories are much larger than what I'm showing, but then the structure is basically the same way. This is as much as I want to get into memories, but then there are RAMs that do not really need all those flip-flops and all the gates and everything. They have something like a let me show you this. They have a word line and a bit line, and then there is only one transistor, and then the capacitor here is really what stores the data into that memory bit. This is the word line. This is the bit line, and again, there is a structure like this, except that the whole memory element becomes what I'm showing here in the circle. Let me draw it here. Capacitor, ground, word line. This is bit line. This is word line, which is the line coming from the decoder, and this is the entire memory element. Okay, in this situation here, the one I'm showing here, you don't need a clock for reading, or you don't need a clock for writing. For writing, you just hold the address long enough for the data to be written. For reading, the same way, you provide the address and you wait for some amount of time for the memory to read that capacitance value and put that on the bit line so it can be sensed by sense amplifiers on this output here. All in all, when we are talking about memories, we are talking about a structure that has address, has input lines, output lines, and a mechanism for writing and reading from it. Next, which we have already said a little bit about, is the bidirectional I/O. And bidirectional I/O is used for several different things, for cascading memories. Okay, let's say I have a memory here. Okay, and this is another memory, and these are the output lines. Okay, let's just assume 3 bits. Structure here, and let's say this is a memory that has 1024. Same thing with this one, 1024. Okay, that means 10 address lines. Okay, if I want to cascade this to make it a memory of 2048, this is how I go about it. I first come up with 11 address lines, take 10 of the address lines to this, another 10 address line, the same 10 address lines to this. Okay, and then I have one address line, the most significant bit. This is bit number 10, and these are bits 9 to 0, 10 address lines. And this is a 1024 memory, this is a 1024 memory, and let's say it has 3 bits only. And then I'll bring this into the chip select logic, and let me do this. This is if it's a 0, okay, that's the chip select input here. If it's a 1, that's the chip select input here. Okay, without getting into the read-write logic, let me continue with what I have here. This chip select, use a different color to make sure the lines are clear. Then this chip select logic goes into this. Okay, and then I'm just showing a very small memory so that we can draw everything here. Okay, so the memory on the left is a 1024 memory with 3 bits, and the memory on the right is the same way, and they both have chip select. Now let's look at this. If my address, or the most significant bit of the address is 0 here, then a 0 here is a 1 here, and therefore the memory on the left will be selected and puts its data on these outputs. On the other hand, if the memory on the let's use this color, if my most significant bit is 1, then this is going to be 0, and therefore the memory on the left is not going to be selected, and only the memory on the right will be putting the outputs on these lines here. Okay, and I had another line that I wanted to draw, which is this one here. Oops. Okay, need a different color, actually this color. Okay, So you're cascading. You're putting two smaller memories, making it a bigger memory. And this is expanding the word length. I'm sorry, expanding address space. And if you were to expand the word length, this is how you would go about it. Again, let's assume that this is a 1024. Okay, by 3. (1024) by 3. 10 address lines, 10 address lines. Okay, 1024 by 3, 1024 by 3. Okay, this has 3 output lines, this has 3 output lines, also 3 input lines. And then you have your 10-bit address here. And then when you have a certain address, you will be selecting a word from here, the same word in the same position from the lower memory. And then this becomes 3 of your bits. This becomes the other 3 bits. And then, in a way, you are merging these. Okay, so 3 bits here, 3 bits here. And then you have a total of 6 bits. The structure on the right, we are expanding the address space. The structure on the left, we are expanding word length. Okay. The one on the right is called horizontal expansion. The one on the left is called vertical expansion. For larger memories, you can actually cascade them in both ways and come up with memories of any size and any address space. All right, so we have shown that tri-state structures can be used for cascading memories, as we are showing here on the right hand side. And we are actually showing, as we showed over here, the bidirectional lines are again for that same purpose. Another use of bidirectional I/O lines is for bus source selection. Let's look at this situation. I have a device with, now we are talking about 3-bit devices, just so that we have a small enough example here. Okay, I have a device that has 3 output lines. This is device 1, this is device 2. Okay, this is device 3. And these devices need to be connected to several other devices. Let's say device 4, device 5, device 6. Okay, and these have inputs. Now, instead of having device 1 connect to device 5, device 1 connect to device 6, device 1 connect to device 4, device 2 to 4, 2 to 5, 2 to 6, 3 to all those, instead of having all those lines, I put a bus in the middle. Okay, I put a bus so that the devices driving the bus will be putting their outputs onto the bus. Devices requiring the bus will be taking inputs from the bus. Perhaps I want to use a different color here. Okay. And then I have a select line for each of these bus devices. Select device 1, select device 2, select device 3. Okay? If device 1 is selected, the contents of whatever I have over here will be driving the bus. If device 2 is selected, the contents of whatever I have over here will be driving the bus. This is the shared bus. And then if device 3 is selected, the contents of that will be driving the bus. I want to make sure that at any one time, only one of these devices will be driving the bus. That means that SD1, SD2, and SD3 are one hot signals, meaning that only one of them at one time can be active. Because if two of them are active, there will be a bus conflict that is called. All right, and then once the source of the buses of the bus is known, then these devices can pick up the data from the bus itself as well. What if these destination devices on the right hand side, also need to provide sources at one point, and also devices on the left hand side also need to get data from the bus at some point. All right, one way would be to have, in addition to these outputs for these buses, also for these devices, also have inputs for these devices. Okay. And then for the devices on the right hand side, we would also need, let me do this in yellow, we would also need D4, D5, D6. We would also need, again, tri-states for getting connected to the bus. Okay. Well, the problem with this is that each device requires in here 3 lines, but in reality maybe 32 lines, 64 lines, 64 lines for output, another 64 lines for input. Okay. Instead of doing all of this, what we can do is we can share inputs and outputs. All right, so what we talked about here is bus source selection, and these tri-states can be used for bus source selection. And what I'm getting into next is we can use these structures for, or the tri-state or the bidirectionals, not only for bus source selection, but also we can use them for bidirectional input and output. So let's go into the next slide. And there I'm going to be drawing perhaps only one device, device 1 and device 4, and then showing how those can both become input and both become output through the same lines. All right, so reducing pin count is this. I have a 3-bit bus. I have a device here, device 1. I have a device here, device 4. I'm assuming device 1 is both acting as input and output. Device 4 is also acting both as input and output. Device 4 has this, providing output to the bus. Device 1. Device 4 has this, getting input from the bus. Okay, but then device 4 also requires some time to put data on the bus. Device 1 has a select that becomes 1 to drive the bus. And then that same device okay. Through the orange lines, it is accepting data from the bus. Through the yellow lines, it is putting data on the bus. Same exact situation over here. Through the orange line, okay, and then this device also has a colors are amazing. So if this becomes 1, then let's just use complete different colors. If this becomes 1, then data will come from the inside of device 4 through this onto the bus. Okay. In that case, we want to guarantee that this other device 1 select input is definitely 0. And then if this is 1, let's see what color I want to use. This one should be good. If this is a 1, then data from here goes on the bus. Data from here goes on this second bit of the bus. And data from the inside of D1 goes on the bus. Okay? I just want to make sure that these two ones are not simultaneously active. Okay, what we have talked about is memories, and we started talking about bidirectional lines, tri-state lines, and then we talked about bidirectional and tri-state lines, and showing that they're good for, actually tri-state lines, they're good for cascading memories. They are good for source selection. This is, by the way, nothing but a multiplexer. And they are also good for reducing the pin count by sharing. This is a true bidirectional bus here that I'm using. And by sharing this bidirectional bus, I'm able to reduce the number of lines of the bus and number of connections to devices by 100%, meaning making them half as many. Okay, this ends this part on memories and bidirectionality.